Hello friends, this is Dr.V Siva Nagaraju, Associate Professor from IARE. Today we are going to discuss receivers. So in receivers we are having two varieties. One is AM receivers and FM receivers. But today topic is AM receivers. Again in AM receiver we are having two varieties. One is tuned radio frequency receiver. Simply we can call it as TRF. And another one is the super-heterodyne receiver. So we are going to discuss these two receivers and what are the merits and demerits of these receivers we are going to discuss in next coming slides. So first, before going to the types of receivers, first what is the receiver? Why? Because in a communication there are three main blocks. The first one is the transmitter, and second one is the channel, third one is the receiver. So we know that the transmitter duty. The transmitter which is going to transmit the signals to the channel, and the receiver which receives the signal from the channel. But actually, whenever the signal enters into the channel, we're not having only the signal. Different types of noises is going to add with our signal. That means our signal is going to corrupt it and it is going to distort it. So here the main function of a receiver is selecting the desired signal from all the other unwanted signals. Why? Because here the desired signal is the wanted one. The remaining all are unwanted. Other than the signal, we can call as unwanted signals. So the first function of the receiver is selecting the desired signal from all the other unwanted signals. After selecting the signal, it's going to amplify. Why? The signal is traveling from a long distances. It is going to distort it. So the amplitude of the receiver is going to weaken. So we are going to amplify first. Then after demodulate, we are come across the original form of the signal. So these are the functions of the receiver. So we know that the function of a receiver is selecting the desired signal from all the other wanted signals, and another one is amplifying, and finally demodulating it. Okay, so this is the function of the receiver. Now types of receivers. So we're having in AM having two varieties. One is a TRF receiver, that is a tuned radio frequency receiver, and second one is super-heterodyne receiver. Now let us start the TRF receiver. So the TRF receiver is a simple logical receiver. So the virtues of this type, which is now not used except as a fixed frequency receiver in special applications, or its simplicity and high sensitivity. So the main advantage of this TRF receiver is its simplicity, having very less number of blocks, and the design of this TRF receiver is also simple. And another advantage is having high sensitivity. This TRF receiver is used at the Second World War time, but presently we are using all our super-heterodyne receivers. Now see this block diagram of this TRF receiver. So here you can see the first one is antenna. We are saying that antenna. So the antenna which is going to receive the signal. That means you are saying that selecting. You are going to select the signal from all unwanted signals. That is done by this antenna. How this is happening? This we are having a RF stage. This RF stage which is going to tuning the signal. So we are going to select the desired signal. And another one is a detector. So we're having RF amplifier, first RF amplifier, second RF amplifier, and detector. Already in the function of the receiver, we know that. First one is selecting the desired signal from all unwanted signals. That is the first function of the receiver. And second one is it is going to amplifying. So second function is amplifying. And third one is demodulate. So here these three blocks are going to gang into each other. That means it is going to mechanically couple each other. So these are the important blocks of this TRF receiver. And then after we're having audio amplifier, power amplifier. So finally it is going to the mark. So this is the block diagram of TRF receiver. So here we're having two RF amplifiers all tuning together. We're employed to select and amplify the incoming frequency and simultaneously to reject all others. After the signal was amplified to a suitable level, it was detected and fed to the loudspeaker after being passed to the appropriate audio amplifying stages. Okay, so this is the function of this TRF receiver. Now, what are the merits of this TRF receiver? So, the first one is the TRF receivers were simple to design. Simple to design. So, that is the first merit. Why? Because here no difficulty. We are having only the amplifier stages and a detector and a mic finally. So, these are the very simple circuits to design. And second merit is they were easily aligned at broadcast frequencies. So what are the frequency range? That is 535 to 1640 kilohertz. So these are the merits of TRF receiver. And again, some demerits also there. So that is the TRF receivers presented difficulties at higher frequencies. So this is the first demerit of this TRF receiver. Why? It is operated at low frequency, you have no problem. But when entering to the high frequencies, there present difficulties. So what is the difficulty? This was mainly because of the instability associated with high gain being achieved at one frequency by a multi-stage amplifier. So this is the first demerit of this TRF receiver. And another one is the TRF receiver suffered from a variation in bandwidth over the tuning range. So this is the another demerit. That is what we can simply called as bandwidth variation over the tuning range. So it was unable to achieve sufficient selectivity at high frequencies. So this is the very important drawback of TRF receiver. That is it having very poor selectivity. You know that the meaning of selectivity. Selectivity meaning it is going to select the desired signal. So it having a poor selectivity. So that's why it can't select the signal at high frequencies. So this was the important drawback of TRF. So that's why we have moved to super-heterodyne receiver to overcome this drawback. What the drawback? That is selectivity. It having very poor selectivity. And encode another problems, that is instability, insufficient adjacent frequency rejection, and bandwidth variation. So giving all these demerits, which reduces the performance of this TRF receiver. So we are moving to super heterodyne receiver. So this is our super heterodyne receiver. So here we can see we're having antenna. Similarly, what that TRF having, and another block is RF stage, and another one having mixer and IF amplifier. So actually, these two, which gives the superior quality for the super heterodyne receiver. That is, the super heterodyne receiver having a high sensitivity and high selectivity. That means it's going to select the desired signal from all unwanted signals. That is done by this IF stage. Okay. And the fourth block is detector, and final is audio and power amplifiers. That is the amplifying stage. So here again, this antenna, which is going to select the signal from all unwanted signals, and then it is coupled to RF stage. This RF stage having RF amplifier, and another one is mixer. Here generally we use down converting mixing, and after mixing we are going to IF stage, that is intermediate frequency amplifier. Simply you can call it as IF amplifier. And another one is a detector block. So this detector, which is going to demodulate the signal and finally apply to the amplifier stage. Okay, and these three, RF, mixer, and local oscillator, which are going to gang each other. It means mechanically coupled each other. So we can simply call it as ganged tuning. Okay. So all the drawbacks in TRF receiver have been removed in a super heterodyne receiver. So already we discussed different demerits in TRF receiver that have been removed in the super heterodyne receiver. So nowadays all receivers are super heterodyne receivers. So what the word heterodyne? Heterodyne stands for mixing. Here we have mixed the incoming signal frequency with a local oscillator. Therefore, this receiver is called as super heterodyne receiver. So in super heterodyne receiver, the incoming RF signal frequency is combined with the local oscillator signal frequency through a mixer and is converted into a signal of low fixed frequency. So here the frequency is fixed. So this low fixed frequency is known as IF, intermediate frequency. So this is the very important operation which is done in this super heterodyne receiver, where what was missing in TRF. Whereas in TRF, it just select the signal, amplifies and demodulate and converts back. So this is the very simple operation of TRF. So that's why it is missing this IF amplifier stage. So that's why the selectivity of this TRF is very less. So we go for super heterodyne receiver. So thus, in a super heterodyne receiver, a constant frequency difference is maintained between the local oscillator signal frequency and incoming RF signals frequency to a capacitance tuning in which the capacitance are ganged together and operated by a common control law. So that we can see in our block diagram. Okay. So the IF amplifier provides most of the gain and bandwidth requirements of the receiver. This means that the IF amplifier determines the selectivity and sensitivity of the super heterodyne receiver. What we missing from the TRF receiver? Okay. After the IF amplifier, the signal is applied at the input of the demodulator, which extracts the original modulating signal. This audio signal is amplified by an audio amplifier to get a particular voltage level. This amplified audio signal is further amplified by a power amplifier to get a specified power level so that it activate the loudspeaker. Okay, so this is the operation of the super heterodyne receiver. Now, what are the merits of this super heterodyne receiver? So it offers superior sensitivity, frequency stability, and selectivity. So compared with the TRF, tuned radio frequency receiver design. So what we missing in TRF, here we get, that is superior selectivity and frequency stability. So this will get by this IF amplifier stage. And second merit of this super heterodyne receiver is it is also offer better stability because the tunable oscillator is more easily realized than a tunable amplifier. So these are the merits of super heterodyne receiver. Coming to demerits. So here also one demerit is there. So one major disadvantage to the super heterodyne receiver is the problem of image frequency. So here we're having one problem, that is image frequency. So in heterodyne receivers, an image frequency is an undesired input frequency equal to the station frequency plus or minus twice the intermediate frequency. So this is a very severe problem in these super heterodyne receivers, and having number of numerical problems depending on this image frequency. Okay. Now we are going to solve some problems regarding in this TRF and super heterodyne receiver. Okay. So let us see. A TRF receiver has to be designed with a single tuned circuit using a 9 into 10 power minus 6 Henry inductor, and the ideal 10 kHz bandwidth occurs at 1100 kHz. So in this problem, we are going to determine the capacitance range of the variable capacitor in the LC tank circuit required to tune the receiver in 550 to 1550 kHz range. And another problem is determine the bandwidth of the receiver at 550 and 1550 kHz. So this is the given problem. We are going to find the capacitance range and the bandwidth of this receiver. So first we take it as a TRF receiver. So for solving this problem, we've taken one formula, that is Q of the LC tank circuit. Why? In this TRF receiver, they use a tune circuit. The tune circuit is designed with L and C. L is a inductor, C is a capacitor, already you know. So by using those two LC, we are taking this Q of the LC tank circuit. So the Q, factor of Q, which is equal to FC by bandwidth. Okay. So we are going to substituting the given values. We get the Q. So the Q value is we get to 110. Why? Because here Q, which is equal to FC by bandwidth. So here taken as FC as 1100 kilohertz and the bandwidth given as 10k. So that's why here 1100 kilohertz divided by 10 kilohertz, you get Q, which is equal to 110. Q value is 110. And now the resonant frequency of the LC tank circuit is expressed as AFC, which is equal to 1 by 2 pi square root of LC. So there is a formula for the resonant frequency. In some people you can use FR in the place of FC, whatever the notation you can use. So at 550 kilohertz, the resonant frequency, the required capacitance value obtained, that value is C, which is equal to 9.31 nanofarad. So we are going to substitute all the values. Why? Because I want to see, that is a capacitance, how much capacitance. So here taken as 550 kilohertz to the left hand side in the place of resonant frequency, and which is equal to 1 by 2 pi. L is given, so you can substitute L value, and after solving this you get C value, that is a capacitance. What is the capacitance of the tank circuit? Why? In TRF we are having a tank circuit. In the problem they ask find the capacitance value. Why? We know that L and C, that we can call it as tank circuit. In that problem they given one Q, that is L value, and going to find another input value is C by using this resonant frequency. Okay. So another one is a radio receiver used in the amplitude modulated system. The mixer translates the frequency FC to a fixed IF frequency is 455 kHz by using a local oscillator FLO. The broadcast band frequencies range from 540 to 1600 kHz. Determine the range of tuning that must be provided in the local oscillator. So they given two cases. One is when FLO is higher than FC, and another one is when FLO is lower than EFC. They given two cases. Okay. So first, before going to solve the problem, here the given problem which related to this, which receiver. First we know that one. Why? Because we're having two types of receivers. One is a TRF receiver and another is a super-heterodyne receiver. So to solve this problem, we know what are the block diagrams and what are the operation of the receivers, we must know. Why? Because here the problem which is given and the application of the receiver. So here there is a applying level. So first we are knowing that receiver operation, and after how to solve this problem. Okay. So here they given two cases. One is FLO, that is local oscillator frequency is higher than FC, and again another one is when FLO, that is local oscillator frequency is lower than FC. Okay. So first when FLO is higher than FC. So what is here 540 to 1600? There is a broadcast band frequencies range. So the frequency range is given, and we know that the formula of IF, how to find IF. Why? Because the given problem is a super-heterodyne receiver. Here the IF stage is missing in TRF, so we can find here the IF is there, intermittent frequency. So IF, which is equal to F0 minus Fs or Fc, what you can use, which is equal to IF. That means the intermittent frequency which is equal to F0 minus Fs. Okay. So that means we're having the low fixed frequency. We get it. So this is done by our mixer. Why? Because the input signal which passes through the mixer, and the mixer having another input as a local oscillator frequency. So this which is going to mix it up and produces this intermediate frequency IF. Okay. So that's why here the intermediate frequency which is equal to F0 minus Fs. So by using that formula, here we are going to substitute this F0 minus Fc, which is equal to 455 kHz. Why? Because here is 455 kHz, which is our IF, intermediate frequency. Okay. So there's FL0, or the local oscillator frequency, which is equal to Fc plus 455. Here we're going to find this local oscillator tuning frequency range. So that's why here F0 or FL0, the local oscillator frequency, which is equal to Fc plus 455. Here actually what is 455? That is 455 kHz is nothing but our IF. So this is 455 kHz, which is nothing but our intermediate frequency. So the local oscillator frequency, which is equal to Fs plus IF, that is signal frequency plus intermediate frequency, which produces local oscillator frequency. Here the given signal frequency range from 540 kHz to 1600 kHz. So this is the signal frequency range. So here we take in two cases. That is when Fc, which is equal to 540 kHz. So first to take the first frequency range is 540 kHz. Then we get FLO, which is equal to 995 kHz. Why? Because here you know this FLO, which is equal to Fc. So what is Fc here? 540 plus what is interval frequency? That is 455 kHz. So when you're going to add up, you get this 995 kilohertz. 995 kilohertz. And the last tuning range of the frequency is 1600. So in this case, this FL0, which is equal to 1600 plus 455. 1600 plus 455 gives 2055 kilohertz. So this is the local oscillator tuning range. So thus the required tuning range of the local oscillator for this case is 995 to 2055 kilohertz. So once again go to see this problem. So in this problem they give an IF frequency, fixed IF, and signal frequency range from 540 to 1600. We are going to find the local oscillator tuning frequency range. Okay. This is the first case. Where the second case, the local oscillator FLO frequency, which is less than FC. So in the previously we solved the first case, that is FLO is greater than FC, but here FLO is less than FC. So in this case, the FLO, which is equal to FC minus 455. So here the FLO, which is we are going to find, and FC or FS, signal frequency, you can say. So FS minus 455. So here also the signal frequency range is same, that is 540 kilohertz to 1600 kilohertz. So this is the signal frequency range or tuning range of the signal, what it may be. So simply it is signal frequency range. Now when FC, which is 540 kilohertz, then what is the local oscillator frequency? So we know that formula, that is FLO, which is equal to FC. Here FC is 540 kilo minus 455 kilohertz. That is a intermittent frequency. Why? This intermittent frequency is a fixed one. It never changes. That is the fixed one. So FLO, which is equal to 540 minus 455 kilohertz, gives this 85 kilohertz. So that is for the second case, that is FLO less than FC. And again, the signal tuning range is from 540 to 1600 kilohertz. So first we are find 540 kilohertz. Again, we are going to find second one is 1600 kilohertz. So that's why here this FC is 1600 kilohertz minus 455, which gives 1145 kilohertz. So in the two cases, we are going to find the local oscillator tuning range. So that's why thus the required tuning range of the local oscillator for this case is 85 kilohertz to 1145 kilohertz. So these are the two cases we solved our problem, the given problem. Okay. So once again, we are going to see the super-heterodyne block. So in this super-heterodyne block, we're having a RF stage, mixer, IF amplifier, and detector. So in the given problem, the second problem, they given this RF stage. That means the signal which is going to tuning. So here, this here taken as Fs. So that is a signal frequency tuning range. And another one is the local oscillator frequency. Here taken as F0. And here produces FIF. So FIF, which is equal to F0 minus Fs. So this is the fixed intermediate frequency from getting the local oscillator frequency and the signal frequency. So that's why in the previous problem they given this IF is a standard one, that is 455 kHz, and they given signal frequency range, and we are going to find the tuning range of the local oscillator. Why? Because here the mixer which is having this local oscillator. So this local oscillator produces this F0 frequency. So in mixer, this F0 which is going to mix up with the signal frequency, then we get this F0 minus Fs. So that is a fixed local frequency. Fixed intermediate frequency. Fixed intermediate frequency we are getting. That is FIF. So this IF is low fixed IF. So it is a fixed one. So what the changing? Here the signal frequency range maybe changes. So according to the signal frequency range, this F0 which is going to change. So that's why here in this problem, the second problem, they given this one. So in this, we're having RF, mixer, and this one is IF stage, and this is a local oscillator. After this IF, we're having detector. So here our importance in this problem is given in this mixer and this IF and the signal frequency range. But generally we taken as signal frequency as Fs and local oscillator is F0 and the intermediate frequency is IF. Okay. But according to the problem we change the notations, but no problem. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.